Hi, everyone. Thank you for coming. My name is Alex Lew, and I'm a PhD student at MIT's Probabilistic Computing project, advised by Vikas Mansinka. And I'm going to talk to you today about a style of declarative programming called probabilistic scripting that my friend and colleague Monica Agrawal has been helping to develop with me. And I'm going to expand on this quite a bit throughout the talk, but the basic idea is this. In the past couple of decades, and especially the last 5 years or so, we've seen an emerging technology called probabilistic programming really begin to take off. There's been a whole suite of tools called probabilistic programming languages that have been developed, and they've primarily been aimed at making it easier to create sophisticated statistical models and AI research. But the core insights that power probabilistic programming and the tools themselves are more broadly applicable than that. And the idea of this talk is to take those insights and that technology and repurpose them a little bit to enable a style of declarative programming that I hope to convince you could be useful for solving many of the everyday problems that software engineers face. So let's look at an example of one of those problems that I'll be using throughout the talk, which is cleaning messy data. This headline is reporting on a survey of data scientists in which they reported that cleaning the data before they got to do the fun analysis part of the data was their most time-consuming, least enjoyable task. This is not like really interesting work. It's the sort of work that any of us in this room could do by hand, of fixing typos, recognizing that numbers are reported in the wrong units, seeing null values that are obviously supposed to be something and filling them in. But it's the work that has to be done before you can actually use your data for something that you care about. So, for example, this is a simplified cartoon example of a data set that we might have if we're running an apartment listings website. Here, we only have 3 columns: the state, the city, and the sort of rent per bedroom that this apartment is being listed for. You can see that this table has some null entries, has some missing entries. And also, if you look at it for a minute and you're familiar with the United States, you'll also see that there are a number of other problems here. A lot of the city names have typos in them, right? They're misspelled. And if you are familiar with the United States, you can probably pretty quickly see what we would have to do to make this a clean data table. Beverly Hills, we know, is in California. Seattle is missing a T, and it's in Washington. New York is not a city in New York State, but New York is a city in New York State. Durham, my hometown in North Carolina, is D-U-R-H-A-M, even though it's pronounced D-U-R-R-U-M. And this middle row, row 3, we can't know for sure what should go in that cell, right? It could be any city in New York. But it's a pretty good bet that it's New York City, for 2 reasons. Number 1, New York City is the most populous city in New York, so if we're assuming that sort of users are coming to our website kind of in proportion to the populations of those states, that would be a pretty good guess. And also, how many cities in New York do you pay $3,000 a bedroom to rent an apartment, right? So humans can do a pretty good job of cleaning this up pretty easily. But this table had 5 rows, and if it had 5,000 rows, even this whole talk wouldn't be enough time to clean it. So we want to automate something. So how do we automate a task like this? Well, we're in a room full of experienced software engineers, and I can imagine many of you might be thinking that automating this task would actually be pretty easy. We're basically dealing with spelling correction in this example, right? And maybe a table lookup to see what state you're in. And in fact, I was at MIT a couple months ago, and there was a professor who was giving a talk on this fancy machine learning-powered data cleaning system that his team had built. And they were using demo data kind of similar to this, with misspelled city names and zip codes that were wrong. And there was a famous Turing Award winner in the audience of that talk. And during the Q&A, that Turing Award winner stood up and asked, to paraphrase, couldn't this be solved by some pretty simple software? I assumed that he was on good terms with the speaker. But you can sort of see what he's saying. It seems like a simple script in Python, or I'm going to use Julia, should do the trick. So let's put that intuition to the test and write a script that cleans up our toy apartment listings data set. We're going to follow a pretty simple algorithm. First, we're going to loop through every row. And our goal is going to be for any row that has a typo in the city field, we want to correct that typo. And for any row that doesn't have a state filled in, we want to fill it in. So the first thing that we can do is in each row, we're going to set the city, we're going to change the city to the nearest actual city, where nearest is comparing edit distance or something like that, of 2 strings. And these possible cities, this possible cities list, is either going to be every city in the United States. If we don't know what state it is, we can't do better than that. or if we do know the state, we're going to limit the possible cities to the cities within that state. If we are missing the state, we have to fill it in. So how are we going to fill in the state? Well, we're basically going to loop through all the states and find a state that has the city that we just inferred was the true city, right? So here's our script. Let's see what happens if we apply this script to our data set. So this was our messy data set. And when we apply the script, we get something a little bit unexpected. It's put Beverly Hills in Missouri, right here in Missouri. It got Durham right. Go Durham. It changed New York, New York to Newark, New York. If you've heard of Newark, you might think it's in New Jersey. And it changed Seattle to Seal. Instead of giving us Seattle, Washington, it gave us Seal, Alabama. So what went wrong here? Well, it actually didn't make any mistakes per se. There really is a Beverly Hills, Missouri, not far from here, in St. Louis County. It's just that it doesn't cost $4,000 to rent a home there. It costs about $800 for a room. And there really is a Newark, New York. In fact, there are dozens of Newarks in the United States. This Newark has a population of about 9,000 people, and it is possible that the user really meant to type Newark, New York. But it's somewhat more likely that they came from New York, which has millions of people in it, and meant to type New York, right? So we could say, we're going to take our script and we're going to try to solve this problem. This is we often debug in a cycle. Debugging is an iterative process. We run our script, we realize it doesn't do what we want, we go back and we change the script. So we could say, let's add heuristics. Let's say that when there's a tie, when two cities could possibly be the city that we're going to fill in, we're going to break that tie with population size, which one has the bigger population. Or we could break ties with which one has a rent that's closer to the rents of all the other entries that have that city in the table, right? We could do something like that as a heuristic. But this leads to longer, harder to read, harder to maintain code, especially if we weren't using a sort of toy example here. Because the people who are reading this code weren't necessarily there when we ran the erroneous code. They might not understand the purpose of all of these extra heuristics. And maybe even more importantly, it doesn't tell us what to do when our heuristics disagree with each other. I have two tie-breaking rules here. Well, we can't use two tie-breaking rules, right? What if they themselves create a tie? So this is what might lead us to ask, is there a better way? And one way of dealing with this problem where your code is sort of growing, it has weird control flow, it has a lot of ifs, is to turn to declarative programming. And there's already been a talk at Strange Loop this year about declarative programming. The idea is that we're going to try to say what we want done, not how to do it. But there's actually a number of flavors of declarative programming. Some of you may have heard of declarative programming in the context of logic programming languages and might think, are you suggesting that we use Prolog for this problem? The problem with Prolog and other logic programming languages, which can sort of solve constraints that you write down, so you say what the constraints you want solved are, and then it will find a logical solution, is that we don't know what logical constraints for this problem are. If we tried to write a Prolog program, it would probably just have the same heuristics, but encoded declaratively instead of imperatively, right? We would say, choose the city with the closest, or the correct city is the city with the rent that is closest to all the other cities, right? That's not really an improvement over what we already had. Another sort of interpretation of declarative could be, and this is a little bit of a weird interpretation, is should we use neural networks? I think of neural networks as a declarative technology because what you actually specify to the neural network is your input and output examples, and then it learns how to actually do the mapping between input and output examples. But that's also not going to solve our problem for two reasons. First of all, we need a lot of training data for a neural net, and we might not have examples of clean and dirty data tables, right, to train this neural net. But more than that, it doesn't even solve the problems that we had, which were hard to understand and hard to maintain. Google, which uses a ton of neural nets, still admitted in this paper, Machine Learning, the High-Interest Credit Card of Technical Debt, that machine learning is a high-interest credit card of technical debt. That when you use it, it gives you short-term gains, you get higher performance, but as the needs of your product evolve, it becomes a lot harder to maintain that neural net in there. When do you need to retrain? How do you keep track of which data set it was trained on? What if we added a column to our data table? Do we have to completely throw away the neural net, which was trained on only some columns, right? There's a lot of questions that it raises to use neural nets, and also, it really seems like we shouldn't need to. This seems like a simple task, right? All of us could do it just by looking at that data table. There's a third kind of declarative programming, probabilistic programming. Should we use that? And you kind of know by the title of the talk that my answer is yes. And the key insight is that we can use probability theory to replace the heuristics that we mentioned earlier with a principled strategy for reasoning about things that we don't know. So let me be a little bit more concrete about that. Probabilistic programming relies heavily on a formula for probabilistic reasoning called Bayes' rule. This is a really important formula in probability theory and statistics, so much so that at HP in Cambridge they made a neon sign of the formula. And you know that when people make a sign for something, it's probably because it's telling us something important. But whereas this sign, it contains a logical formula. If you hit this sign, then you will hit that bridge. This sign, the Bayes rule sign, contains a probabilistic one, telling us how to reason about things that we don't know by combining domain knowledge with observations. So let's take a closer look at what it's saying. There's 3 letters involved in this formula, an A, a B, and a P. So A is going to represent the unknown variables that we're trying to reason about. B is going to represent our observations, what the user actually typed in the row. And P is going to represent all of our domain knowledge. So to make this concrete, let's say that we're trying to clean this row, the Beverly Hills $4,000 row. What are our knowns and unknowns? Well, it might seem that our knowns are the city and the rent, and our unknown is the state because it's empty. But remember that we're not assuming that the user typed the city correctly. For all we know, Beverly Hills could be a typo of Beaver Hills or Beverly, right? So really, we should think of this as having 2 knowns and 2 unknowns. The dirty city, the potentially dirty city, and the rent are our known things, our observed values, and the unknowns are the state and the clean city. The other letter in this formula is P. This is a probability distribution or a model, and the idea is that it's going to encode our domain knowledge about this data set, all of the assumptions that we bring to the table that allow us to clean this data set, right? When I was showing that slide, I said, we are familiar with the United States, we're familiar with how cities work, we know what an apartment listings website is. All of that is knowledge that was helpful to us when we were cleaning the data set. So P is going to somehow have to encode that knowledge. The types of things that P is going to have to encode involve, for example, the idea that more populous cities and states appear more often. This assumption allowed us to disambiguate between Newark, New York, and New York, New York, right? And it tells us which values of the unknown variables are more likely a priori. No matter what the rest of the row says, we kind of believe that cities that are more populous are going to appear more often. There's also kinds of domain knowledge like this, that per bedroom rents in a city and state tend to be similar across listings, right? And this is what allowed us to choose Beverly Hills, California as more likely than Beverly Hills, Missouri, because Beverly Hills, California had a $4,000 rent. That made sense, whereas Beverly Hills, Missouri, that wouldn't have made as much sense. And note that this particular piece of domain knowledge connects unknown variables, city and state, with the observed variable rent, telling us how our observations depend on the value of the unknown variable. And that's going to allow us to reason about which possible unknown values actually explain our observations better, right? Make our observations more plausible. Another type of domain knowledge that falls into the same category is the way that cities and typed cities are related, which is that typed cities may rarely be a typo diversion, or may rarely contain an edit from the actual city. And in fact, even more rarely, they may contain multiple edits, right? Multiple typos. So we bring all of this domain knowledge to the problem. And some of the domain knowledge, which I'm going to denote P of A, is domain knowledge telling us which values of A, which values of our unknown variables are just more or less likely, unrelated to the rest of the data, right? But the other pieces of our domain knowledge, called P of B given A, tell us for a particular value of A, so you should think of that A as actually being filled in with Beverly Hills, California, or Beverly Hills, Missouri, right? For a particular value of A, what distribution over B does it induce? What does it tell us about which observed values would be more likely or less likely to see, given that we're already in, that we know that we're in Beverly Hills, Missouri? So these 2 types of information tell us what do we expect before we even see the row about which cities and states are going to be likely, and how should we think about the observations that we made in terms of how likely they would be made by different possible hypotheses for what the unknown values are. What Bayes' rule does is give us a principled way of combining all of these kinds of domain knowledge with our observations. It says if you're trying to find A, let's say we have a few hypotheses for A, like it could be Beverly Hills, California, or it could be Beverly Hills, Missouri. If we're trying to decide what A is, we should score each of these A's according to this formula. P of B given A times P of A. It's basically multiplying how likely is A in the first place by how well does it explain the data B? Right? It's going to allow us to trade off between these two components. And so what we're going to do is we're just going to take each of our hypotheses, compute this multiplication, and see which one is higher. So in this case, I haven't told us how to give numbers to these things yet. We're going to get there. How can we actually make this quantitative? But even looking at this qualitatively, we can see that P of Beverly Hills, California has to be greater than P of Beverly Hills, Missouri, because Beverly Hills, California is a more populous city. Beverly Hills, Missouri has about 500 people. And over here, there are sort of two things that are playing into this. There are two observed values, the typed city and the rent. Now, the typed city, Beverly Hills, is made equally likely or is explained equally well by both of our hypotheses. Because in both of our hypotheses, Beverly Hills is the actual city name that the person meant to type. And in both of the hypotheses, 0 typos were required to get us to Beverly Hills. But the rent is explained much better by the top row than by the bottom row. And so overall, we're going to say that this whole thing, the top row is better than the bottom row, and we can choose Beverly Hills, California. And this insight that data cleaning can be framed as probabilistic inference and application of Bayes' rule was described and made formal in a paper just this year called A Formal Framework for Probabilistic Unclean Databases. But it's one thing to recognize that probability theory might be useful, which is sort of what we've done so far in this talk. And it's another thing to actually make it concrete and code something up. What is the programming model that's going to let us actually apply these insights, right? We haven't even described yet how to make these qualitative P's quantitative, right? So probabilistic scripting is going to give us a declarative programming framework for applying probability theory to problems like this. In the data cleaning example, what that's going to mean is that we're going to want to come up with some way to encode in a script the domain knowledge that we have, this P. Then we're going to want to be able to feed in a messy data set and have the cleaning happen automatically, right? So we want whatever task we're doing to happen automatically given the domain knowledge that we've encoded in a script and the actual observations that we have. So we're trying to replace these heuristic imperative scripts with probabilistic declarative scripts that say things like more populated cities appear more often, rents of different listings in the same city are likely similar, right? So we have to find some way of making a scripting language that allows us to encode these sorts of statements. And before we look at the way to do that, it's worth noting that there's reason to believe this is sort of the right way to solve the problem, which is that if you actually go out to organizations that have big data cleaning needs, like the Department of Energy, they have tons of data sets coming from all over, and they need to clean all of these data sets, they have slide decks where they train lots of humans in how to clean data. And if you look at what they don't say, if you see a number that is above this threshold, please divide it by 1,000. What they say is, you might see inconsistent units of measure. You might see, instead of thousands of square feet, which is what we want, you might see total square feet. You might see, instead of million cubic feet, you might see therms of natural gas. So it's just telling you what sorts of data you'd expect to see and how you might expect them to be wrong. And they're assuming that the people will use common sense. The people who they're training will use common sense to interpret that data and use it to sort of come up with an algorithm for how they're actually going to clean the data set. So we need to do exactly that. We need a flexible way for users to encode knowledge. We can't just show our computer a slide deck. And we need an efficient way to actually do the cleaning, for our computer to do the cleaning after we convey the knowledge. And this first challenge, how do we make a scripting language for encoding domain knowledge? Let's remember that this is the kind of knowledge that we want to encode in our script using a programming language, but not English. And let's recall that we've already seen how these different kinds of knowledge can be thought of as helping to specify distributions, probability distributions, telling us what values are more likely or less likely. Or more concretely, what cities and states are more likely or less likely. Or given a city and state, what typed cities and rents are more likely and less likely. And the main insight that we're going to borrow from probabilistic programming is this. If we write a program that randomly generates cities and states, so imagine that this table is just from calling a program over and over again to randomly generate cities and states. We have implicitly specified a distribution over cities and states. The ones that the simulator or the generator is more likely to have generated are more probable, and the ones that it is less likely to have generated are less probable. So we've written down a distribution by writing a program that randomly generates cities and states. Similarly, we can write a program that takes in a particular city and state and randomly generates a rent and randomly adds typos to the city to generate a typed city and a rent. And in doing that, we've specified a probability distribution over typed cities and rents that depends on the particular city and state that we're in. So in order to encode that more populated cities appear more often, we can write a program that randomly samples cities according to their populations. So that when we run it, we get cities like New York and Los Angeles much more often than we get cities like Durham, North Carolina. To encode that rents depend on the city, we can actually randomly generate a rent based on the city. So that if we do this by adding noise to some average rent for the city, rents for the same city will cluster together. And in order to encode that city names might contain typos, we can just randomly choose some of the city names that we generated, or for each city name, randomly decide to add typos or not, with some small probability. So that's the idea behind this probabilistic scripting DSL called Pclean for data cleaning that we have. What does this look like in code? So we've created a little scripting language. It's embedded in Julia, and it's specifically for writing generators, random generators of data, to encode domain knowledge. And once we fill in the blank lines here of our rent row generator, we're going to be able to call this clean function on a table and have it automatically clean the data. And we'll talk about how that works as well. But let's look at how the simulator looks first. So in order to say that we're generating a value for a column, we use this @column keyword. We give the name of the column that we're currently generating. And if we want, we can give a variable name so that we can hold on to the value that we simulated. And here I'm just going to call this choose proportionally function, where I pass in a list of all the states and a list of their populations, and it will choose a state proportionally to the population. Now you might be thinking right now, I listened to 20 minutes of this talk, and now you're telling me that this won't work if I don't know the state populations? Because it seems like that would be a pretty serious limitation once we go to the sorts of problems where we don't necessarily have data that we can download from the government. But we're going to get to in a minute how we're going to relax that assumption that we have all of this information available. For now, let's focus on the concept that if we can write this generator, we'll be able to do the cleaning. So we're going to choose a state proportionally to the populations of the states. We're going to choose a city proportionally to the populations of the city. And notice here we're just saying that the cities that are possible to choose come from like a dictionary map called cities, mapping particular states to the lists of cities that they contain. Right? So it's going to be impossible for our script to generate a city that doesn't belong to the state that it generated. Right? But that's not the city that we're actually going to see. So there's also this @dirty construct, which says, even though the true city has already been sampled, now I'm going to generate a new value, which is an edited version of that, which represents the sort of way in which it might be unclean. Right? So we are assuming that our city might have typos, so we're going to call this add_typos function. And if you look inside that add_typos function, what it's doing is it's flipping coins with 10% probability of heads. And if it comes up tails, we're done, we leave the city as it is. If it comes up heads, we add a random typo to the city, a random insertion, deletion, or substitution. Right? And then, once we've added the typo, we flip another coin. Same coin with 10% probability of heads. And if it's another heads, we add another typo. If it's tails, we're done after adding one typo. So what this does is it encodes that we think there's a 10% probability of there being one typo, a 1% probability of there being two typos, and so on. Okay. Finally, we're going to sample the rent, and here I'm assuming that we have access to this list of mean rents in all of the cities and states in the United States, so that what we can do is just add some noise to it, where 100 is the sort of average variation. It's the standard deviation of that noise. So once we've written this script, we can run clean, and it will apply Bayes' rule for us, happily cleaning our data set. No messy heuristics needed. It will incorporate all the possible factors in making a decision. It's going to incorporate the edit distance between the typed city and the real city, because we have that add_typos in there. It's going to incorporate the plausibility of the rent value given the city and state. And it will incorporate the populations of the cities under consideration. And we haven't told it how to do that. We haven't written control flow to do that. We've just told it what we know, and it's going to automatically weigh all three of those factors to come up with an answer. But like I said, there's still something unsatisfactory about this, which is that we had to hard code a number of things. We had to hard code the state populations. We had to hard code the city populations. We had to hard code the mean rents. And we also hard-coded this number 100, which is sort of how much do rents vary within a city. Right? Now, it's worth noting that humans actually do bring a lot of this information to the problem. Right? The reason that we were able to look at just 5 rows of data and clean it is because for our whole lives we've been learning that rents are expensive in New York. Right? For our whole lives we've been learning that what cities exist in the United States. Right? Things like that. and which states have bigger populations and which cities have bigger populations. So it might be unfair to expect a computer to solve this task without that lifelong experience, but if we can't solve the problem, that's sort of fatal for this approach, because many domains don't have government data sets telling us exactly how likely different values of the columns are. So in Pclean, we allow users to replace those parameters with underscores, and then call this fit function to learn the parameters from the messy data table itself. In essence, the fact that we have a big table of data can stand in for the computer's lack of life experience. It can pick up all this knowledge by looking at patterns in the data that you give it, right? And in particular, the way that this learning is actually going to work is that it's going to begin by choosing some initial values for all of those parameters, just setting some initial values. And then, assuming that those initial values are true, it's going to clean the data set completely. Then we're going to get a completely clean data set from which we can re-estimate the parameters and do this in a loop. And this is an algorithm called expectation maximization. And it will eventually, it should eventually converge to some values of these parameters. Also notice that these parameters, these underscores, are allowed to have square brackets after them, indexing by some expression. And what that's saying is that a different value of this parameter should be learned for every value of the index, right? So we're able to then communicate that the rent per bedroom doesn't have just one mean that noise is added to. It has a different mean for each city and state. Okay. Now we're still saying here that we're giving it the list of cities that exist and the list of states that exist. And this might seem like a more reasonable assumption. We often do know what the possible values for some column are, but it's kind of annoying to compile, and sometimes we don't know it. So Pclean is also going to let you replace that with an underscore. And that means that it should learn which of the things in that column are actually valid values and which ones were just erroneous. So for example, if we have a big data set and only one row has this city Newport in it, the system is going to compare the hypotheses that, on the one hand, it's possible that there is a city called Newport, because we haven't told it what cities exist. So it's possible that there is a city called Newport, but if that were the case, it would have such a small population that only one entry from this table came from it. And so then it's comparing the probability that we got the one citizen of Newport versus the possibility that one of the millions of citizens from New York made a typo, right? And so it's going to correct it to New York. On the other hand, if we have several rows called Newport, and the rents are very low, now the calculus kind of changes, because on the one hand, it can consider the possibility that all of these people made this typo, same typo, and that they somehow all happen to be the ones who got the cheapest rents in New York. Or it can consider that there actually is a small city called Newport in New York that has cheap rents, right? And in this case, it will prefer the second hypothesis, right? And none of this came from us explicitly coding these heuristics in. Pclean is based on probability theory, which is the lingua franca of a lot of research in data science. So I want to show you one cool benefit that we get kind of for free by using probability theory here, which is that we can benefit from some of the latest advances in AI to create more expressive models. So I don't know if you've seen, it was in the news a while back that OpenAI had trained this huge language model called GPT-2. They said it was so good at generating language that it would be dangerous for them to release it to the world. So they've been going on this like small release strategy where they release slowly more accurate models. So this is based on one of the medium models that they've released, what I'm going to show you. And the idea is that you can prompt this neural network with a string. It can be a pretty long string. So here I've put the abstract of this talk, ending with, in this talk, I'll introduce. Okay? And it's going to complete that string for us using what it's learned from billions of documents over the web. So it chooses to say, in this talk, I'll introduce X table, which enables common sense reasoning to code up automated fixes and checklists to automate common errors and get your data clean faster. Don't worry, it includes a free demo. So. I don't appreciate it making promises on my behalf. But the idea is that since this is actually just all based on probability theory, all of these numbers that we need in order to add one of these primitive distributions are available to us from GPT-2. So we can add a new distribution called GPT-2 elaborate, a new primitive that we can use in our models that's going to take in a prompt and return a completion, an elaboration of that string according to GPT-2. This allows us to model new kinds of data sets. So here's a data set of reviews. It has 3 columns: whether a review is positive, what the product type being reviewed is, and the actual text of a review. And these are actual Amazon reviews. And you can see some of the cells are missing. So what we can do is we can write a Pclean script that says, okay, here's how the data is generated. First, we flip a coin. I don't know what the weight is to determine whether we're going to write a positive or negative review. And I don't know the weight because maybe people are more positive or more negative in general as a whole. Let's not assume anything by writing 0.5 or something like that. Then we're going to choose a product type, and we'll just learn what product types exist by looking at the table itself. And we'll learn what proportion they occur in. And then we somehow want to say, write a review that's based on is positive and the product type. And the idea is that we're going to use GPT-2 elaborate on some prompt to do that. We're going to prompt GPT-2. We could use the prompt, the following is my review, and then just have GPT-2 write a review. But then GPT-2's review will not be based on the sentiment and the product type that we just sampled, right? There's no relationship between these two. So we could instead say, the following is my review of this book, or of this movie, or of this app. And that's going to make it more likely to generate reviews that are about the product. But we want to incorporate the sentiment too, so we can switch on the sentiment with an if statement and say, if we're trying to generate a positive review, we're going to prompt it by saying, I'm giving this book a very positive review because it's fantastic. A+, 5 out of 5, best book ever. And otherwise, we're going to say, I'm giving this book a very bad review because it's awful. F, 1 out of 5, truly terrible, worst book ever. And then we're going to pass that to GPT-2 to finish off the review. Okay? Once we've done that, once we've encoded our assumptions about how the review text depends on the other columns, right? Pclean can figure out that this was a positive review about a book or a negative review about a movie. And we didn't have to do any additional training. We didn't have to train a neural net with a bunch of labeled examples. All we had to do was specify the task by writing up this prompt and writing up this script. Right? So I said there were 2 challenges. We've looked at the first challenge. The second one I'm going to spend less time on because I want to spend another 5 minutes or so. This task that I'm calling cleaning in this example more generally is called probabilistic inference. It's about how you infer the values of unknown variables given domain knowledge and your known variables. And it's one of the things that probabilistic programming languages give us a lot of tools to do. So the architecture of Pclean, how it actually works, is that we take this script that the user has written and we compile it into a probabilistic model in a general purpose probabilistic programming language called Gen. And we're also going to extract some metadata from this script that Gen wouldn't know about because they're sort of things that are specific to data cleaning. So we're going to extract from the script sort of what fields are clean, what fields have the possibility of being dirty, which fields have parameters, which were these underscores, what our initial parameter values are. We're going to infer sort of, there's also stuff that I haven't shown about missingness. We're going to get metadata about sort of aspects of the parameter estimation process, because none of that is sort of built into Gen. But what we get by having this probabilistic model represented in Gen is that it gives us the ability to evaluate probabilities, to express the operation of conditioning our simulator on known observed values, and most importantly, it gives us a library of building blocks for approximate inference. And this is something that couldn't have been done until very recently, because for a long time, probabilistic programming languages were just push button, just like Pclean is. You specify your model, you say clean, and you hope that the algorithm, you say infer, and you hope that the algorithm can handle your model. Right? In Gen, instead, it gives us a library of building blocks where we can construct our own inference algorithm, and the inference algorithm behind Pclean is making use of that. We're using several of the building blocks together to create an inference program that combines sequential Monte Carlo and expectation maximization by using these building blocks. It's something that Gen calls programmable inference. And there was another talk at Strange Loop yesterday by my colleague Marco about that. So feel free to go online and look. It explains sort of the new programming constructs that enable the expression of these kinds of inference algorithms. The nice thing about Pclean, and in general, I hope, about sort of these domain-specific probabilistic programming languages, is that once you've restricted yourself to a certain domain, you can reason much more effectively about what sorts of inference algorithms will always work in that domain. And so the idea is that this inference algorithm, though I'm sure that we still need to work on it some, should be applicable to most of the models that people write in Pclean, because Pclean isn't quite as expressive as Gen as a whole. Right? We have some preliminary results, very preliminary results, sort of showing that these existing machine learning-based systems for data cleaning, we can match them if we just encode some basic domain knowledge into our scripts. But I want to zoom out a little bit at the very end, because my point today isn't primarily about Pclean or data cleaning. It's about this broader idea of probabilistic scripting. And the basic point is that if you have some code that's imperative and relies on a bunch of heuristics, right? It's often because you're trying to do something common sense that the computer doesn't have the declarative knowledge in order to solve. Right? That's what's getting you into this mess. And if you can frame your task as reasoning about unknown variables in the context of domain knowledge and observed variables, then we can think about actually replacing this with a much more natural sort of scripting approach, where you just tell it what you assume to be true. And your normal computer would say, what am I supposed to do with that? But we have replaced it with a robot that has read a probability theory textbook. By which I mean we have replaced it with a robot whose internals are to compile into one of these powerful general-purpose probabilistic programming languages, get some metadata out, and then run an inference program. Okay? And the idea is that this should work whenever you can frame your problem as an inference task with domain knowledge, unknown variables, and observed values. So if that sounds appealing to you, I encourage you to play around with Gen yourself and help invent new probabilistic scripting languages. The language is open source and embedded in Julia, and in addition to the API documentation, we have a number of tutorials available in this Gen Quick Start repository. And I want to thank all the members of the ProbComp team. This wouldn't have been possible without them. I also want to thank Strange Loop for holding this awesome event and letting me come here and share this with you. And also, this project is funded in part by the Facebook Probability and Programming Research Award. So I want to thank them. Thanks.